Welcome again, STEM students. Today we will be discussing the following: physical quantities, units, and measurements. Our discussion will be divided into the following outline: physical quantities, units, measurements, accuracy versus precision, random versus systematic error. After discussing each topic, you are expected to accomplish the following objectives. Number 1, solve measurement problems involving conversion of units and expression of measurements in scientific notation. Number 2, differentiate accuracy from precision. Number 3, differentiate random errors from systematic errors. And number 4, estimate errors from multiple measurements of a physical quantity. Let us start the discussion by defining and describing physical quantity. Physical quantity is a property of a material or system that can be qualified by measurement. In physics, when we say property, it is synonymous to characteristic. Therefore, physical quantity serves as an adjective for different materials and systems which we will encounter as we move to different topics in physics. Physical quantity can be expressed as the combination of a magnitude and a unit. Magnitude pertains to the numerical value which tells us how much a physical quantity is. Unit gives meaning to the magnitude by serving as an identifier. For example, we are able to know that 100 degrees Celsius describes temperature because of the unit degrees Celsius. Without the unit, the number 100 will be meaningless. Physical quantity is represented by symbols, usually English alphabet or Greek letters. Physical quantity can be classified as fundamental or derived. Physical quantity can be classified as scalar or vector. Let us further expound on each of these 3 points in this slide. Physical quantity is represented by symbols, usually English alphabet or Greek letters. Representations through symbols are quite necessary when physical quantities already belong to equations. Here are some examples of English alphabet used as symbols to represent physical quantities. We may use uppercase. For example, the uppercase letter P symbolizes the physical quantity power. We can also use lowercase. For example, the lowercase letter D to symbolize distance. Most of the time, the first letter of the physical quantity becomes its symbol. However, there are exemptions that we will encounter as we study physics. Here are the examples for Greek letters used as symbols to represent physical quantities. For uppercase, we have uppercase Greek letter phi or phi, which symbolizes flux. And for lowercase, we have lowercase Greek letter tau to symbolize the physical quantity torque. You are already familiar with the English alphabet, but I think most of you are not yet familiar with the Greek alphabet. Here are illustrations to show you the different letters in the Greek alphabet, both the uppercase and the lowercase. I highly suggest that you familiarize yourselves with them because you will surely encounter some of them in our future discussions. Letters can also be combined with numbers to differentiate one quantity from another. Here are some examples of letters combined with numbers as their subscripts to add meaning to the quantities. Example number 1. P sub 1 symbolizes magnitude of momentum before the collision. And example number 2, P sub 2 or P with the subscript 2 symbolizes magnitude of momentum after the collision. Our keywords here are the before and after. In physics, we study changes. When something changes, there is an initial condition and a final condition. In other words, changes involved a before and, of course, an after. Usually, number 1 as subscript denotes the physical quantities involved before the change, while number 2 as subscript represent the physical quantities involved after the change. Let's have example number 3. T sub 1 or T sub 0, also read as T naught, symbolizes initial temperature. By the way, the naught is spelled as N-O-U-G-H-T, and it literally means 0. Let's have example number 4. Example number 4 is T sub 2 or simply T, which symbolizes the final temperature. When naught is used as subscript for the initial value, we no longer put a subscript to the final value. Aside from letter and number combinations, physical quantities may also be represented by combining letter and another letter as subscript. Here are some examples. Example number 1. M sub A or M subscript A symbolizes mass of object A. A represents any matter involved in the problem. It can be B if another matter is involved. It can be C, D, and all other letters of the English alphabet. If the situation involves 3 matters, we may use A, B, C as subscripts. If 10 materials are involved, we may use letters A to J as subscripts and so on. Example number 2, the phi sub E symbolizes electric flux. The capital letter E that serves as the subscript, as you can see on the slide, represents the word electric. And for example number 3, we have phi subscript B which symbolizes magnetic flux. For some reason, scientists decided that uppercase letter B should represent magnetic field. So to distinguish electric flux from magnetic flux, the subscript B is used for magnetic flux and the subscript E is used for electric flux. I have decided to divide this lesson into 2 so that you will be able to digest each part of it. That was part 1, and I highly encourage you to tune in for part 2, wherein we expound on the fact that physical quantities can be either fundamental or derived, or it can also be either a scalar or a vector. That's all for physical quantities discussion part 1. Tune in for part 2.